Hello everyone. In this video lecture we are going to discuss about the notch filters, which are kind of compensators used in order to avoid the high frequency oscillations. In many mechanical systems we have high frequency vibrations. You can see an example over here, and this is because of the presence of the poles in the vicinity of the imaginary axis. Basically, these poles will have a small real value and they might have big imaginary value, and they will introduce the high frequency oscillations that you can see over here. Once we have this case, then designing a controller in order to satisfy especially the transient requirements will not be an easy task. Okay, so let's have a look at how we can design the notch filters by using an example. Here we have the definition for the notch filter. A notch filter is basically a set of zeros and a pair of poles. The poles will be located on the real axis with let's say big real values, negative big real values, and the zeros will be located at the vicinity of the poles, which result in the high frequency oscillations. In this way, the notch filter will kind of cancel the effect of those poles, or in other words, the frequency of the oscillations that we have over there will be filtered. That's why it is called the notch filter. This is indeed a kind of band pass filter. Another approach would be to keep the controller gain low, at a low value, but then as we see in the example, in that case the response of the system might not be fast enough for us. Okay, so we can't just keep the proportional controller with a low value for the gain, because the transient requirements might not be satisfied. So let's see how a notch filter could be designed. We have an example over here. You can see the transfer function given in the form of 2500 over s times s plus 1 times s squared plus s plus 2500. Over here we have a pair of the poles s1 and 2, which are located at minus 0.5 plus minus j50. So the location of the poles could be shown over here. Poles and zeros of the system. We have a pair of the poles at the vicinity of the real axis with a small value for the real value and big value, relatively big value for the imaginary values. So minus 50j plus 50j and minus 0.5, and we have one pole at minus 1 and another one at the origin, they are 0. And we want to design a controller such that the steady state error for the constant reference is equal to 0, MP for the step response is smaller than 30%, and the 2% settling time is smaller than 1 second. The first requirement is already satisfied because we have a type 1 system, and therefore the steady state error for the step reference is already equal to 0. So we don't care about the first requirement. And we need to check the other two, MP and the settling time. Let's have a look at the Root-Locus of the system. I already have it over here. Let me maybe go back to the full view. So you can see in the full view the kind of in the Root-Locus that we have for the system. Basically, I can redraw it over here in it, just to give you an idea of how it will look like. So the two branches will originate from the pole at the origin and the one at minus 1. Then they will depart their real axis. We will have two branches originating from the complex pose. They will meet at some point, let's say over here, and then they will go towards the infinity using the asymptotes. So this will be somehow the Root-Locus drawing for this system for positive values of k. You can see that for a given value of the rho or gain, for rho between 0 and let's say rho star, the system will be stable. For rho bigger than rho star, the system will become unstable, and that will happen over here. So we can't increase the value of the gain more than a given value. You can come back over here. Let me just change the values for the axis in order to have a closer look. For the y-axis, I'll keep the values between minus 55 and 55, so you'll have a closer look. And in terms of the x-axis, let's keep it between minus 5 and 1. Okay, so you can see that part of the Root-Locus indeed. And in the upper part, you can see the step response of the system. So I guess you can already see that the settling time for this system is quite high. It is around 23 seconds. And we want to have it smaller than 1 second. Okay, so let's come back here. I can introduce the design requirement. For the settling time, we want to have 1 second. So it means that we should have the closed-loop pose on the white area. And for the overshoot, we need to have it smaller than 30%. So we should manage to keep to bring the closed-loop pose of the system into the white area over here. But let's see before that what happens if we try to increase the gain of the controller. I can just move it. You can see that as I increase the gain value, the settling time started to decrease. It decreased to around 11 seconds. If I increase it further, you can see that the settling time will be around 8 seconds, but we already have started to have oscillations. If we increase the gain a bit more, you can see that the frequency of the oscillations increases, and the settling time is still around 8 seconds. If I continue increasing the gain, you see that we will have still the high frequency oscillations. The settling time is still around the given value. If you continue to increase the gain, settling time increases and the frequency of the oscillations increases as well. And if we try to increase it further, the system will become unstable. So with a proportional controller, we cannot satisfy those requirements. Yeah? It's not possible to satisfy the requirements in terms of the overshoot and also in terms of the settling time. You can also see let me see if I can bring yes, you can also here see the overshoot. It's basically around 100% for this value of the gain. Changing the value of the gain will change that value for the overshoot, yeah. But you can see that with a proportional controller, we are not able to satisfy those requirements, while we are happy with the steady state requirement. Okay, so in order to improve the transient behavior, let us use a compensator with a 0 at minus 4.56, and a pole at minus 70. And I hope you know that this is a lead compensator. We are going to improve the transient behavior. We are trying to do that, yeah? Let's do it. Let me see if I have it already over here. I have a 0 at minus 4.56 and a pole at minus 70. Here we have the step response of the system. With that, okay, let me remove this. We have the settling time and the overshoot, and we can try to change the value for the gain, yeah? Now we are happy with the overshoot. It is 22%, which is below 30%, but the settling time is more than 4 seconds. I can try to increase the gain in order to decrease the settling time. Let's see what happens. Let me increase it over here. Instead of 3.67 in this format, I can try to have 6. Let's see what happens with 20. Oops, just made a mistake. With 20, it's already unstable, so let's go back to 6. Okay, I hope you can see it, yeah? In terms of overshoot, we are fine, but the settling time didn't decrease, and we have high frequency oscillations present. We can try to go a bit further, let's say 7, but you already see that these two poles are approaching the right half plane, and eventually our system will become unstable. In this case, you can see that the settling time now is increased quite a lot. It's around 40 seconds. So we kind of need to cancel the effect of these poles first, yeah? If we do so, if we cancel the effect of those poles by using a notch filter, then we might be able to improve the settling time, keeping the overshoot below 30%. To cancel the effect of those two poles at minus 0.5 plus minus 50J, we will place a pair of zeros at minus 0.5 plus minus 51J, so they will be pretty close to the poles that we have here. And then for our notch filter, we need to have two poles on the real axis. We will place them at minus 80 and minus 85. And then we will see what happens to the response of the system. So let's go back to our controller. We also need to adjust the value that we have for the gain. Let's introduce two real poles for our notch filter. One at minus 80 and the other one at minus 85. And complex zeros. The real part is minus 0.5 and the imaginary part is 51. Okay, so one more thing that we need to do here is to change the the form that our controller is displayed into events form. In terms of the, looks like it didn't take, I have two Root-Locuses indeed. Displayed. We go back here. Okay, now we have it. In terms of the gain, we need to set it at 2640. And you can see the step response that we have here. The overshoot is below 30%, and the settling time is 0.54 seconds. If you look at the Root-Locus plot of the system, you can see that those two poles that we had, and they were creating the high frequency oscillations, they are nearby zeros, and those zeros are canceling the effect of those poles in it. That's why you don't see the high frequency oscillations anymore over here. So in this way, we can deal with those kind of systems by introducing a notch filter to our system, and afterwards we can design the other kind of control that we need to satisfy the transient requirements, which could be generally a lead compensator. Alright, so that's all for this video. Thank you for watching, and see you in the next video.